There is a submarine somewhere in the Western Pacific right now. A Virginia-class attack boat, roughly $4 billion of American engineering, nuclear-powered, carrying torpedoes, cruise missiles, and one of the most sophisticated sonar suites ever built. And trailing behind it, somewhere between 200 and 900 meters astern, is a cable. A thin, oil-filled cable, slightly thicker than a garden hose, studded with hydrophone sensors along its length, dragging through the water at whatever slow speed the captain has chosen for the day. That cable is the TB-29 towed array. It was developed from concepts first proven in the 1970s. The physics behind it have not fundamentally changed in half a century. And on a hull that costs more than the GDP of some small nations, that cable, that Cold War relic, is the primary tool the boat uses to detect a threat before the threat detects it. Here is the paradox this video is going to sit with for the next 25 minutes. The Virginia class carries an AN/BQQ 10 spherical bow array, one of the most capable passive sonar systems afloat, processing acoustic signals with computing power that would have filled a warehouse in 1985. So why does the skipper deploy a fragile, speed-limiting tow cable to do work that a multi-hundred-million-dollar bow array supposedly handles? And what happens when the answer to that question puts the boat in a corner, forced to choose between hearing far and moving fast, in exactly the stretch of water where both matter most? The answer has layers. The layers have costs. The costs have a logic that takes time to unfold. To understand why the towed array exists on a modern nuclear submarine, you have to understand what sound does in seawater and what it refuses to do. Sonar is the art of listening. A passive sonar system makes no sound of its own. It receives. It picks up acoustic energy radiating from another vessel. The low-frequency rumble of a propeller, the hum of pumps and machinery, the faint cavitation signature of a hull moving through water at speed. The ocean is not empty. It is full of acoustic noise. Shipping lanes, biological sounds, the creak and groan of the seafloor, thermal gradients that bend and scatter sound waves in ways that are partly predictable and partly not. Finding a quiet submarine inside that noise is, depending on the day and the water, somewhere between very hard and nearly impossible. The physics that govern how far you can hear in the ocean are captured in something called the SOFAR channel, the sound fixing and ranging channel, a layer of the ocean at roughly 300 to 1200 meters depth, where temperature and pressure combine to create a minimum sound speed zone. Sound waves refract toward this layer from above and below, bending back in, and in ideal conditions, they can travel hundreds or even thousands of kilometers trapped in this acoustic waveguide. This is how the US Navy once tracked Soviet submarines across entire ocean basins during the Cold War, using fixed hydrophone arrays on the seafloor called SOFAR, the sound surveillance system. A Virginia-class submarine operating in the Pacific does not have access to a fixed seafloor array under its keel wherever it goes. What it carries is the AN/BQQ 10, a sphere of hydrophones packed into the bow, roughly a meter in diameter, processing signals across a wide frequency band. In good water conditions, with a quiet target, this array can detect a nuclear-powered submarine at ranges measured in tens of kilometers. In bad water, shallow, warm, thermally layered, biologically noisy water, that range compresses dramatically, sometimes down to a few kilometers or less. The South China Sea is bad water. Shallow, warm at the surface, heavily trafficked by commercial shipping, and thermally stratified in ways that create acoustic shadow zones. Volumes of water where a receiver simply cannot hear what is happening because the sound waves have been bent away. The choke points where a Virginia class would most likely operate, the approaches to Taiwan, the Luzon Strait, the passages between the Philippine island chain, are exactly the kind of environment that punishes bow-mounted sonar. This is the first layer of the paradox. The most expensive component of the boat's acoustic suite is physically located in the noisiest part of the boat. The submarine's own propulsion plant, its pumps, its reduction gears, its hull flow noise. All of it propagates forward and leaks into the bow array's reception. The array's signal processors work constantly to subtract the boat's own self-noise. But self-noise is the fundamental limit on what a bow array can hear at speed. Go faster, hear less. The physics are unforgiving and they apply to everyone. The towed array solves this by getting the hydrophones out of that noise environment entirely. Tow a long cable several hundred meters astern, and you have placed your ears in water that the submarine's own machinery cannot easily reach acoustically. The TB-29, which replaced the earlier TB-16 and TB-23 variants, is a thin-line array roughly several hundred meters long when fully deployed. It listens in very low frequency bands, below a few hundred hertz, where sound travels farthest and where diesel-electric submarines tend to leave their most detectable signatures, however faint. The economic dimension makes this choice even starker. A single TB29 towed array costs in the range of tens of millions of dollars. The submarine trailing it costs somewhere between $3.5 and $4 billion per hull, depending on the build variant and when in the Virginia-class production run you are counting. One relatively cheap sensor dramatically extends the effective acoustic reach of a platform that would otherwise be partially deaf in precisely the water it needs to operate in. That is the logic. But the logic has a shadow. Let us talk about what the Virginia-class is actually hunting. The People's Liberation Army Navy, PLAN, has been building submarines at a pace that American naval planners watch with sustained attention. The PLAN submarine force includes nuclear-powered attack boats, ballistic missile submarines, and a large conventional force of diesel-electric boats. Among the conventional types, the Type 039. The Song class and its descendants represents the main patrol submarine threat in the Near Seas region. The Type 039A and 039B variants incorporate air-independent propulsion, or AIP, which is a fuel cell or Stirling engine system that allows the boat to run submerged for extended periods without snorkeling to run its diesel generators. What that means acoustically, a Type 039 running on AIP is close to silent. There are no diesel engines, no generator noise, no high RPM components radiating energy into the water. The boat moves slowly. AIP systems are not powerful, but slowly and quietly is exactly what you want when you are waiting in a choke point for a carrier strike group or a Virginia class to pass through. The acoustic signature of an AIP-equipped Type 039 at low speed is in the characterization that appears in open-source naval literature among the quietest submarine signatures in the world. Not because the technology is exotic, but because a boat that barely moves and barely makes noise is hard to hear. What is most surprising about this problem is not the Chinese submarine. It is the geometry. The Virginia class is a superb hunter of nuclear submarines, which radiate noise continuously because their reactors, coolant pumps, and propulsion plants never stop running. A nuclear boat at low speed is still a heat engine with moving parts, and moving parts make sound. The Type 039 on batteries is a different problem. Intermittent, quiet, patient, and capable of sitting in a thermal layer at periscope depth in shallow water for hours without making a sound worth detecting. This is the asymmetry that keeps US Navy sonar operators focused. A 40 to 50-year-old concept. The diesel electric submarine. Upgraded with AIP and modern silencing, running at 3 or 4 knots in layered coastal water, is genuinely difficult for even the best passive sonar to reliably detect at tactically useful ranges. The TB29's low-frequency reach is the best tool available to extend that detection range, but deploying it has a price. The obstacle is not the sensor itself. The TB29 is a reliable, well-understood system. The obstacle is speed. A towed array cable, streaming astern at the end of a tow cable hundreds of meters long, is not a rigid structure. It moves. It vibrates. At speeds above roughly 5 to 10 knots, turbulent flow around the cable and its hydrophone housings generates hydrodynamic noise that floods the array's own reception. Self-noise, again, but now from the sensor rather than the hull. Above roughly 8 to 10 knots, the TB29's low-frequency detection capability degrades significantly. Above 12 to 15 knots, it may as well not be deployed. So a Virginia class running the TB29 at full acoustic effectiveness is doing roughly 4 to 6 knots. That is a fast walk. In a submarine, 4 to 6 knots is the speed at which you cover ocean very slowly, and it is the speed at which you cannot respond quickly to a tactical development. If a contact appears on the port bow at 4 knots, repositioning to gain a better bearing takes time, minutes to tens of minutes, not seconds. And this is where the geometry problem compounds everything. A single towed line array has no left-right discrimination on its own. A sound arriving from the port side and a sound arriving from the starboard side at the same bearing angle are mathematically ambiguous to a single line. The array cannot tell them apart. This is the port-starboard ambiguity problem, and it has been known since the first towed arrays were deployed. The solution is maneuver. The submarine turns, and by changing its own heading, the geometry of the array relative to the contact shifts, resolving which side the sound is coming from. But turning takes time. And maneuvering while towing a long cable requires care. Towed arrays can kink, and a kinked cable can be damaged. Turn too sharp, too fast, and you risk fouling the array entirely. I spent considerable time going through the open-source operational literature on towed array doctrine, and one detail kept surfacing. The time penalty for resolving a contact is not a minor inconvenience. In a contested choke point, a passage between islands where the water is shallow and the geometry is constrained, the time required to maneuver, resolve the ambiguity, and classify a contact can exceed the time the contact spends in detection range. You hear something. you start to turn. By the time you have a bearing solution, the Type 039 has moved or descended into a thermal layer or gone back on batteries and slowed to 2 knots. The window closes. This is what naval analysts mean when they describe the towed array dilemma as a real tactical constraint, not just a textbook footnote. The array extends detection range dramatically in open, deep water. In the shallow, thermally complex, geometrically constrained water of the Western Pacific island chains, those advantages partially offset against a set of penalties that the platform's designers cannot fully engineer away. Let us put some structure on what the economic exchange actually looks like. A Virginia-class Block V submarine. The current production variant, which adds the Virginia payload module for additional cruise missile capacity, runs to approximately $3.4 to $4 billion per hull. The US Navy has been procuring them at a rate of roughly 1 to 2 per year in recent budget cycles, constrained not by desire but by submarine industrial base capacity. The 2 yards that build Virginia-class submarines, General Dynamics Electric Boat in Groton, Connecticut, and Huntington Ingalls Industries Newport News Shipbuilding in Virginia, are running near their physical limits. The TB-29 towed array, by contrast, is a consumable in relative terms. Units cost in the range of tens of millions of dollars. They are depreciating assets. Cables wear, connectors corrode, hydrophone elements degrade over deployment cycles. The Navy maintains stocks and replaces them. The economic logic is straightforward. A relatively inexpensive sensor that extends the survivability and effectiveness of a $4 billion hull is one of the best investments in the fleet. The problem is that this logic only holds as long as the sensor is deployable. And in the tactical environment we have been describing, deployable is not always the same as effective. Here is the part that does not make sense on the surface, and yet the doctrine leans into it anyway. A Virginia-class captain in a contested patrol area is routinely making a choice that has no clean answer. Slow down, deploy the array at full effectiveness, gain detection range, and accept that the boat cannot reposition quickly if the tactical picture changes. Speed up, increase tactical mobility, gain the ability to sprint and drift or respond to a fast-developing contact, and partially blind the boat's best long-range acoustic tool. Sprint and drift is the operating concept that tries to thread this needle. The submarine runs at speed for a period, listening on its bow array, accepting reduced effectiveness, covering ground. Then it slows to drift speed, deploys or lets the towed array stream, and listens at low speed for a defined interval before sprinting again. The logic is that you trade continuous maximum range acoustic coverage for tactical mobility, cycling between the 2 states. In open ocean transit, this works reasonably well. In a choke point where the geometry constrains your sprint legs to a few miles, the calculus tightens uncomfortably. Here is something worth putting on the table, though it will probably generate pushback. The towed array, by design, trades the submarine's greatest tactical asset, stealth through mobility, for acoustic reach. A slow submarine in contested, shallow water is not just partly deaf when it speeds up. When it slows down to listen effectively, it is also easier to detect by an adversary with its own passive sensors, whether submarine, surface ship, or maritime patrol aircraft. The Type 039 sitting quietly at 4 knots in a thermal layer is not the only one with acoustic patience. Planned surface combatants, including the Type 054A frigate with its own hull-mounted and variable depth sonar, plus maritime patrol aircraft operating from Hainan Island and purpose-built bases in the South China Sea, create a multi-layer acoustic picture that a slow-moving Virginia-class must account for. What this tells us about the broader competition is worth pausing on. The plan has invested deliberately in layered anti-submarine warfare, not to match the Virginia-class unit for unit, but to complicate the environment in which it has to operate. More patrol aircraft, more surface combatants with towed arrays of their own, more distributed underwater sensors along key transit corridors. The goal is not to defeat a Virginia-class in a straight acoustic competition. They probably cannot do that. The goal is to raise the cost of operating quietly in the near seas region high enough that the American submarine has to make harder trade-offs. The towed array dilemma is, in part, a product of that strategy working as designed. Put yourself in the shoes of a Virginia-class commanding officer for a moment. Not in the strategic abstract, but at a specific decision point. You are in the Luzon Strait. Water depth is variable, between 200 and 800 meters, depending on where exactly you are. Your intelligence brief tells you there is a Type 039A operating somewhere in your patrol area. You have the TB-29 streamed. You are doing 5 knots. Your sonar team has a possible contact, low confidence, bearing ambiguous, range unknown. To resolve the ambiguity, you need to maneuver. To maneuver with the array deployed, you need to do it carefully and slowly. Your executive officer notes that a planned Type 054A frigate is conducting exercises roughly 40 miles to your northwest. Do you stay slow and resolve the contact, accepting the positioning risk? Or do you haul in the array, sprint to a new datum, and try to reacquire from a different geometry? Accepting that you may lose the contact entirely, there is no doctrine answer that eliminates this trade-off. There is doctrine that guides how to weight it, and that doctrine, in general, favors acoustic caution over speed in a search phase. The logic is straightforward. A submarine that has not detected a threat is more dangerous than one that has. The cost of losing a contact because you move too fast is potentially the cost of being surprised. And in submarine warfare, surprise has historically been terminal. But the doctrine also acknowledges that a submarine staying slow too long in a contested area accumulates a different kind of risk. Maritime patrol aircraft, specifically the P-8A Poseidon, which the US Navy operates extensively across the Pacific, can drop sonobuoy fields that passive listen across large areas. A Virginia-class holding position at 4 to 6 knots for an extended period, within range of a planned maritime patrol corridor, is a submarine that has made itself predictable. Predictable submarines get found. The P-8A Poseidon operates from bases across the Pacific, Kadena Air Base in Okinawa, Misawa in northern Honshu, and deployed from forward locations depending on the operational requirement. Its acoustic mission is to sanitize patrol areas ahead of surface groups and to cue submarine forces. When a Virginia-class is operating in coordination with a carrier strike group, a USS Carl Vinson or a USS Theodore Roosevelt transiting the Philippine Sea, the P-8A's sonobuoy fields provide some degree of overwatch that reduces the cost of the submarine's speed dilemma. The boat does not have to do all of its own acoustic search. The multi-layer picture helps. But it does not eliminate the fundamental physics problem. Here is where the industrial dimension enters the picture and changes the shape of the problem over time. The US Navy currently operates around 50 Virginia-class and Los Angeles-class attack submarines. The Los Angeles-class, older boats, many of them nearing retirement, carry a different towed array configuration and have less processing capability than the Virginia. The Virginia-class fleet is expanding, but slowly. Congressional Budget Office analysis and Navy budget documents suggest that the Virginia-class production rate, currently around 1.2 to 1.5 boats per year depending on the budget year, is below the rate needed to maintain the planned fleet size as Los Angeles-class boats retire. The 2 submarine shipyards are at capacity. Expanding capacity requires investments in facilities, workforce, and supply chain that take years to materialize. The submarine industrial base has been a recurring topic in congressional testimony from Navy leadership, including the Chief of Naval Operations and the Secretary of the Navy, for several consecutive budget cycles. The constraint is real. There is no surge option for submarine production the way there might be for some surface combatants. A Virginia-class takes roughly 7 years from contract award to delivery. The workforce to build them is specialized and takes years to train. Against this, planned submarine construction has continued at a pace that has caught the attention of the Office of Naval Intelligence. The total planned submarine force, across all types, is assessed to be larger than the US Navy submarine fleet by count, though not necessarily by capability. The Type 039 series alone numbers in the range of several dozen active boats, with additional units under construction. Numbers do not tell the whole story in submarine warfare. One Virginia-class with full crew proficiency in good water is worth multiples of a less capable diesel boat in many scenarios. But in a specific choke point, in bad water, with a quiet AIP Type 039 doing what it was designed to do, the capability gap narrows in ways that the towed array trade-off reflects exactly. Now close the loop. We opened with a paradox. A $4 billion submarine relying on a Cold War cable to do what its modern bow array cannot. The answer is not that the bow array is deficient. It is excellent, and in its designed operating environment, it performs accordingly. The answer is that the designed operating environment and the actual operating environment in the Western Pacific are not the same thing. The AN/BQQ-10 spherical array is optimized for deep water, open ocean acoustic conditions. The Virginia-class was designed during a period when its primary mission was to track Soviet nuclear-powered submarines across the North Atlantic and the Norwegian Sea. Deep water, known acoustic environments, adversaries with continuous acoustic signatures. The mission has shifted. The threat has shifted. The water has changed. The towed array is not a workaround for a failed bow sonar. It is a physics-dictated complement to a bow sonar that was never designed to dominate shallow water choke point search in the first place. The TB29's length and its low-frequency sensitivity give it aperture, the physical size of the receiving array, that a bow-mounted sphere cannot match. Longer array equals better angular resolution at low frequencies equals greater ability to separate a quiet contact from background noise. That gain is real, and it is not available from any bow-mounted system that fits inside a Virginia-class hull. Physics sets the floor. The cable is not a sign of technological inadequacy. It is the answer physics gives you when you ask how to hear quietly in difficult water. But this is exactly where the doctrine lives. The physics that make the towed array valuable are the same physics that impose the speed penalty. The cable has to be long to be effective. A long cable at speed becomes a noise source. A noise source drowns out the signal the cable was deployed to detect. The Virginia-class, therefore, faces a constraint that cannot be engineered away with better processing or newer electronics. To use its best sensor at full effectiveness, it must accept a mobility penalty in the exact tactical environment where mobility matters most. The strategic cost of this situation is not measured in a single incident or a single patrol. It is measured in tempo, in crew, and in decision space. Crew tempo is the least discussed but most real constraint. A Virginia-class deploys for roughly 6 months at a time. Submarine crews are among the most intensively trained personnel in any navy, a qualification pipeline that takes years and cannot be accelerated quickly. The stress of sustained patrol, weeks of acoustic watch, the constant cognitive load of operating a nuclear reactor in contested water, the isolation, is cumulative. The Navy manages this through the blue-gold crewing concept, where 2 crews rotate through a single submarine hull, but the number of hulls limits the number of operational patrols regardless of crew availability. Fewer submarines mean fewer patrols. Fewer patrols mean thinner coverage of the Western Pacific. Thinner coverage means the trade-off the Virginia-class captain faces in the Luzon Strait is made under conditions of higher operational demand, not lower. Decision space is the strategic abstraction that underpins everything else. A Virginia-class captain choosing between slow and listen and fast and mobile is not making a purely tactical choice. That choice ripples upward. Whether a carrier strike group can transit a given strait with submarine escort providing acoustic screening, whether a potential adversary can assess that the approaches to Taiwan or the Philippine Sea are sanitized, whether the deterrence calculation that both sides are making in a period of heightened tension has the friction of uncertainty in the right places. Submarines work by making their presence felt without being seen. A submarine that is slow and predictable reduces the ambiguity that deterrence depends on. A submarine that is fast and mobile reduces the acoustic coverage that the slow one was providing. Neither is a free move. One detail that stays with you after thinking carefully about this. The TB-29 and its predecessors were designed when the primary threat was a Soviet nuclear submarine. A platform that makes continuous noise, operates in deep water, and can be tracked over long ranges with confidence. The AIP diesel electric threat that the TB-29 now primarily hunts in the Western Pacific is almost the opposite in every relevant characteristic. Quiet, shallow, intermittent, patient. The sensor is older than the threat it is being asked to defeat. That is not a failure of the sensor. It is a reflection of how fast the threat environment moved and how hard it is for complex, expensive hardware programs to keep pace. Here is the take that will probably draw some argument. The United States Navy's submarine advantage in the Western Pacific is real, but it is narrower in the near-seas environment than a raw capability comparison between a Virginia-class and a Type 039 would suggest. Not because the Virginia-class is inadequate, it is not, but because the environment in which that capability has to operate constrains it in ways that do not show up in a comparison of specifications. The Type 039 is not trying to beat the Virginia-class in deep water on a clear acoustic day. It is trying to be hard to find in the water where it lives, doing the thing it was built to do. And that is a fundamentally different problem than the one the Virginia-class was optimized to solve. The TB-29 is the Navy's practical answer to that problem right now. The next-generation alternatives, distributed undersea sensors networked to surface and airborne platforms, unmanned underwater vehicles operating as acoustic pickets, perhaps eventually AI-assisted signal processing that finds the AIP contact in noise that a human sonar operator cannot, are in development, in testing, in early deployment. The Large Displacement Unmanned Undersea Vehicle program is one thread of this. The Orca XLUV, built by Boeing, is designed to operate for extended periods in exactly the kind of persistent surveillance role that a towed array on a manned submarine handles today at high crew cost and tactical risk. But these systems are years from replacing the function the TB-29 serves, and the force structure gap in the submarine fleet exists right now, not in a projected future. So here is where the Doctrine actually lands, and why it matters for anyone watching the Western Pacific closely. The Virginia-class captain in the scenario we described. Luzon Strait, Type 039 contact, frigate to the northwest, will, according to the doctrinal weighting, almost certainly choose the acoustic patience option. Hold slow, work the contact, resolve the ambiguity. Accept the positioning risk, manage it with situational awareness from the P-8A overhead and whatever surface picture intelligence provides. The contact takes priority over the repositioning. That choice is not universal. It is context dependent. In a declared emergency, if the battle space has shifted to active hostilities, if a contact has become a weapons solution problem rather than a search problem, the calculation changes entirely. But in the grey zone competition that defines the day-to-day reality of US submarine operations in the Pacific today, acoustic caution is the standing preference. Here first. Everything else follows from that. What this means going forward is that the towed array trade-off is not going away. It is structural. It will persist until a fundamentally different approach to persistent underwater surveillance in the Western Pacific closes the gap. And that is an investment story measured in billions of dollars, years of development, and industrial capacity that does not yet exist at the required scale. The question to leave with you is not whether the Virginia-class is good enough. It is. The question is about the choice the captain makes at 4 in the morning in the Luzon Strait, with a low-confidence contact on the TB-29 and a planned frigate 40 miles away. Slow down and hear farther, or speed up and cover ground. Both choices have a real cost. Both choices leave something unprotected. Tell us in the comments which call you would make, and then think about what it means that there is no answer that avoids the trade-off entirely. The next time you hear that the US Navy has the most capable submarine force in the world, that is true. And the cable trailing behind a $4 billion boat is the clearest evidence of exactly how hard it is to keep it that way. If you want to understand how the surface fleet tries to pick up where the submarine leaves off, the Arleigh Burke destroyer's sonar suite, the towed arrays it deploys, and the coordination problem between surface and subsurface ASW, that is the next piece in this series. It starts where this one ends.